Okay, so I want to look at some arithmetic and geometric series, which is basically the sequences except you're adding all the terms. And in this, I'm using sigma notation in the examples here, but really the first thing I'm going to do is get rid of the sigmas. So let's see if this works. Yeah, okay. So the idea of the sigmas is I'm going to start with the general term 4 plus 3k. I'm going to plug in 0 first. So 4 plus 0 is just 4. And then I'm going to increase all the k's one at a time and add up all those terms until I get to k equals 12. So the next term will be 4 plus 3 times 1. And then the next term will be 4 plus 3 times 2. And then that'll keep going until I get to 4 plus 3 times 12. Like that. Okay, and so the goal is to add that all up, and that's long enough where it's annoying to do it all on a calculator, so it would be useful if we could come up with some sort of trick for it. So here's what I'm going to do. I'm actually going to write out the first few terms. That'll be 4 plus 7 plus, let's see, what's this one going to be? 10 plus, and then dot, dot, dot. In fact, let me do this. I'll even include the 11th term here just so we have it, and then the 12th term, because that'll actually make this a little easier to see. So this will be 4 plus 33 will be 37, and then this one will be 36 plus 4, 40. Okay, so this is my sum right here. I'm going to call it S for my sum. And what we know is we've got a total of 13 terms here, because if you notice, this actually isn't the first term. It's the second term. This one's the third term. So this one would be the 12th term and the 13th term. So 13 total terms. So what I'm going to do is I'm going to write the same sum, but I'm going to write them in reverse order. So I'm going to put 40, 37. Let's see, the one that would come before that would be 34. And then if I go all the way to the end here, the last two terms would be 7 and 4. Now, one of the great things about an arithmetic sequence is that when I add it to itself and I've lined these up backwards like that, I get 2s, and then every single term here ends up being exactly the same. And remember, we have 13 of them. So this really becomes 13 times 44. And then I can divide by 2, and I get 13 times 44 all over 2. So it's 13 times 22. And I don't have a calculator. I don't care what that is. You guys can figure that out. That's easy enough now. Okay, so what I want to do is I want to come up with a general way of what we just did, right? Because then we'll have a formula for all arithmetic sequences. Let me move this one out of the way for now. Okay, so an arithmetic sequence is one where the first term is just whatever it is. The second term is the first term plus some new amount called the common difference. And then I'm going to keep adding another d to that. So the next term will be a1 plus 2d, and then a1 plus 3d, and so on. And the nth term would be a1 plus n minus 1d. Okay, now I'm not going to write it out with all the d's first. I'll come to that at the end, but this will be useful to reference. So if it's arithmetic, and it's got to be arithmetic to use this trick, sequence series, sorry, because we're adding everything. And it's got to be finite. If it's infinite, this isn't going to work either, because you keep adding more and more and more to it. It's not going to work. If it's infinite, then it just goes on forever and it explodes. So it'll diverge. So this one, finite arithmetic series, what I'm going to do is I'm going to write out the sum as a1 plus a2 plus dot 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 plus an minus 1 plus an. So notice here there are n terms here. And then I'm going to write the same thing backwards. Right? Now, remember the nice thing about this if it's arithmetic, only arithmetic, is that when I add these up, these are going to be the same as these, which are going to be the same as these, which are going to be the same as those, and same as every single pairing that I make there. And they're all going to be the same as a1 plus an, the first term plus the last term. And there are going to be a total of n pairings of them because I have n terms in each one. So, up to here. So this I can multiply by n. Now I'm going to take s and divide both sides by 2. So I get n over 2, a1 plus an. So really all you would need is the first term, the last term, and the number of terms in order to figure out what the sum is of an arithmetic series. But sometimes the last term's sort of annoying to get, so that's where this comes in handy. Because if I substitute that in for the last term, then I get s equals n over 2, a1 plus a1 again, plus n minus 1 times d. So then this turns into n over 2, 2a1 plus n minus 1 d. And so you have two different formulas on your note sheet. One of them is this one, and one of them is this one. And they both work. This one is often a little bit better because then you just need the difference, the total number of terms, and the first term. You don't actually ever need the last term out of it. Whereas this one, you would actually need to know that last term. Okay. So geometric sequences, I think, are actually a little bit, in my opinion, they're a little bit easier, but it's up to you how you want to think about it. This would end up being 10 times a half to the 0, which is really just 10, plus 10 times a half to the first, plus 10 times a half squared, plus dot dot dot, plus 10 times a half to the 7th. So if you think about it, this has 8 terms, right? So I'm going to call the sum 10 plus 10 times a half. I'm not even going to multiply those in. I don't want to because it'll actually make things harder for me when I try to do the trick that I'm about to show you. So the trick is, I'm not going to add another s and reverse the terms like I did for the arithmetic. I hope you realize this one's geometric series. And this trick only works for geometric ones. So if I actually take the s and I multiply it by the same thing that I'm multiplying all these guys by, a half, then this 10 becomes 10 times a half. And this 10 becomes, or this 10 and a half, 10 times a half becomes 10 times a half times another half. Everything gets multiplied by a half. So this term turns into 10 times a half, which I'm going to line up with this one. And then when I take a half and I multiply it by the second term, I'm going to get 10 times a half squared. And if I keep that process going, I'm going to get, when I multiply 10 with the half to the 5th, I'm going to get 10 times a half to the 6th. And then when I multiply this one by a half, I'll get 10 times a half to the 7th. And then when I multiply the last term, I'll get 10 times a half to the 8th. So now the nice trick is, I'm going to subtract them. Right? Whoops. And if I subtract the top from the bottom, I get s minus a half s. I get 10 minus 0. And then this cancels, this cancels, this cancels, this cancels, and I'm left with the 0 that's left up here minus this term. So minus 10 times 1/2 to the 8th. So then this side I can factor. I'm actually going to write this in kind of a weird way first. So this becomes 10 minus 10 times 1/2 to the 8th. And then I'm going to divide out the 1 minus a half. Divide out the 1 minus a half. And here's my sum. And you can plug that into a calculator to figure out what that actually is. Now, notice that this is the same thing as the first term minus the first term times the common ratio. And it's raised not to this power, but one more than that. So if I have, let's see, how do I want to write this? Yeah, I'll say to the n here. Let's say to the n. And we'll check that in a minute. And that's going to be over 1 minus the common ratio. Okay, so let's prove that using just general stuff. General stuff here. So in a geometric series, the first term is just whatever it is. The second term is the first term times some common ratio. The third term is going to be the first term times the common ratio to get the second term, and then times the ratio again. And then I'm going to multiply a3 by the ratio one more time, and then it'll continue up to the nth term, which will be a1r to the n minus 1. So if I write out the sum, a1 plus a1r plus a2r squared, or sorry, a1r squared, plus dot 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 plus a1r to the n minus 1. So there are n terms here. And what I'm going to do is I'm going to multiply s by r. So I get, instead of a1, I get a1 times r. And instead of a1r, I get a1r squared up to a1r to the n minus 1. And then when I multiply this by r, it becomes r to the n. So now I'll do what I did before and subtract. And so I've got s minus rs. And then I've got a1 minus nothing. And then these guys cancel. And then I've got 0 here minus ar to the n. a1r to the n, let's say. And then I can take out the 1 minus r. Or factor out the s, I mean. And then divide. And that's proof that that's the sum of a finite geometric series. All right, sometimes you see this written in factored form instead, like this. That's pretty common too. Okay, I hope that